In the second part of continuity, we're going to talk about discontinuities a little bit more. So the first thing we'll look at is what a removable discontinuity could look like. So usually it means that we just have to fill in a hole in the picture. So for example, that would be an example of a removable discontinuity. And so would this one by moving that point back in to fill up that hole. The thing about the removable discontinuities is the limit actually exists because when I approach from either side, they agree, but it's the function that does not agree. So for a removable discontinuity, the limit exists, but the function is not the same. For non-removable discontinuities, we mentioned these already. We had a jump, and we also could have things like an infinite discontinuity, where there's an asymptote and they're discontinuous because they just end up going on becoming infinitely large. The other thing we can have is an oscillating discontinuity. Now it might appear that this graph is, say, smooth like a sine curve and that you could move your finger smoothly along it, but there's actually lots of gaps in it. So I'll show you one example of how an oscillating discontinuity works, just to give you an idea. So I'm a little short on space here, so I'm just going to open up a new page. But here's an example for oscillating behavior. Let's just say that my function, let's just say that my function was the sine of 1 over x. And I'm interested to know about the limit as x goes to 0 of the sine of 1 over x. So as you probably started to realize, it's not always so straightforward whether this exists or not, because it's the limit. It's not that it would be undefined to divide by 0, but there are cases where the limit exists, and that's what we want to know is, does this exist or not? So I'm going to give you an example of why this does not exist. So I'm going to give you some points that are approaching 0. For example, if you think of the sine graph, I'll show you my strategy here. Here's the sine graph. This is pi over 2, and this is 3 pi over 2. So if I looked at the reciprocals, I could do 2 over pi, then I could do 2 over 3 pi, and I'm going to keep moving along, going 2 over 5 pi. I keep hitting these points on the graph every time it repeats. So the next one will be 2 over 7 pi, and maybe I'll stop here and you'll get the point. The top is the same for all of them, it's 2, but the bottom keeps getting larger. Pi, 3 pi, 5 pi, 9 pi, etc. Eventually, you know, somewhere down here, it'll be 2 over like 1,000,000 and 1 pi. Is that right? Well, anyways. So it's going to be getting closer and closer to 0. So this sequence of numbers I picked approaches 0 just like the limit does. But if I was to look at the values, at 2 over pi, it's going to take the reciprocal. It's going to be pi over 2, which is here, at 1. But at 3 pi over 2, the reciprocal is 2 pi over 3. It's going to be negative 1. And then when I hit 5 pi over 2, the reciprocal is 2 pi over 5, so I got 1. Negative 1, 1, negative 1. It keeps doing that over and over and over again. So the closer I get to 0, I'm not approaching any single value. The closer I get, the faster the points oscillate between 1 and negative 1. So of course that's a problem because the limit, in order for it to exist, has to go to just a single value. But this one, that's why you see as it gets closer and closer, it starts going try a better graph there. It starts going more and more crazy like this. Right? So even though it looks like the graph might have a nice smooth line to it, it's actually going to start jumping like this the closer you get. Anyways, that's an oscillating graph as an example. So let's take a look at this continuity and identify its discontinuities. So in this graph here, there's a jump. There's a removable here. But everywhere else the graph would be defined as continuous. Now this is more typical of what you'll expect to encounter on the AP exam, is a piecewise graph. It may possibly be in a picture, but something like this where you're expected to talk about the continuity just based on the algebraic definition. So what you want to know is, basically you can guarantee that this piece is continuous and this piece is continuous because they're both polynomials. So all I'm worried about is, do they meet? Because here is the left side, I know it's continuous. The right side's also continuous. So all I need to know is, does the limit as x approach 1 from the left equal the limit as x approaches 1 from the right? If it does, that means those two pieces meet up. And I know it's continuous. So one of them is a parabola, the other is a line. So roughly, I'm talking about a graph that'll look kind of like this. So it either connects like that, or possibly it's something like this where there's a jump. Okay. So to figure that out, which one of those cases it is, the limit as f of x goes to 1 from the left side, it's going to be negative 2 times 1 plus 3. That's equal to negative 2 plus 3, which is 1. As I go from the right side, that's going to be equal to 1 squared. I'm using the functions over here. So 1 squared, which is 1. So both agree. So yes, they do meet. This graph is continuous everywhere. So if we apply the same ideas to the second graph, this is a continuous function everywhere. So is this. This is my only concern, is what happens at x equals 2. So I'm going to take a look at the limit as x goes to 2 from the left, which is going to be the limit as x goes to 2 from the left of negative 2 times x. So it's going to be negative 2 times 2, which is negative 4. And if I look at the limit as x goes to 2 from the right of f of x, this time I'm looking at the limit as x goes to 2 from the right of x squared minus 4x plus 1. So this will be 2 squared minus 2 times 4 plus 1. So 4 minus 8 plus 1, and that looks like I'll have negative 3. So these two values are not the same. It means there's going to be a jump because they don't touch. So this one is discontinuous. Whoops. Discontinuous. Why don't we say jump discontinuity to be more specific? At x equals 2. So in the final one, again, we're thinking of the same values. For x plus 3, continuous everywhere. For this one, you might be concerned about the square root, but on these values from negative 3 to 3, it's defined everywhere. So this is, again, a continuous function. Same thing here, you might be worried about dividing by 0, but it's not in the domain. So this is, in fact, also a continuous everywhere function. So the only problem I might have with continuity is where they join. That's at negative 3 and at positive 3. Those are the pieces where they would fit together. So the first time I have to take a look at the limit as x goes to negative 3 from the left, f of x, which is the limit as x goes to negative 3 from the left of x plus 3. So that's 0. If I look at the limit as x goes to negative 3 from the right side, I'm now on this function. So it would be (3 minus square root of 9 minus x squared). So that'll be 3 minus the square root of 9 minus 3 squared. So that's going to be 3. This one here is 0. So there must be a jump discontinuity there because they don't meet. And let's take a look at this piece here. So we already know what the value is as we approach negative 3. This time we're focusing on the other part to join up, which is at positive 3. So I'm going to take a look at the limit as x goes to 3 from the left of f of x. And on the left side, it's going to be approaching from this graph here. So this is going to be the limit as x goes to 3 of 3 minus root 9 minus x squared. So 3 minus root. So we end up with the same value. This goes to 0. And so we end up with 3. So it won't affect our answer, but there should have been a negative there. Okay. Then we need to do the limit as x goes to 3 from the right side of f of x, which is the limit as x goes to 3 of 1 over x, which is 1/3. So again, those two pieces, there will be a jump discontinuity because they do not meet. So when you have a jump discontinuity, when you're looking for that, what it means is that the limit from the left side exists, but is not equal to the limit from the right side, which also exists. So both the left hand and the right hand limits exist, but they don't agree on what the value should be. So the last thing we're going to take a look at with continuity is the intermediate value theorem. It's kind of a theorem that it's fairly intuitive. It's not really something that I want to spend a lot of formal time defining. But basically what it says that if you have a continuous function, on a closed interval, then what we can say is that we know we have the points here for, this is B, let me just see, sorry, that's A and f of A, and this is the point B, f of B. Then what we could say is for every value so that it's between A and B, I'm just going to change something here for a second. Instead of, probably be easier to write this down instead of using f of c. Let's call this, let's call it v for value. That'll work. So let's just say that you have some value in between f of a and f of b. Then it must be somewhere in the interval. Now, I don't want you to stress too much about the formal definitions. But basically what it means is if I was to run my finger from A to B, because this is a continuous graph, I have to assume every value in between. So for example, this is f of b here, and this is f of a here. Now, no matter what value I pick in between there, it must be present in the graph. So for example, if I just randomly stop here, then there's the value on the graph. If I randomly stop here, there's the value on the graph. And I can keep doing this. It must be present. The only way it would not be present, if you think about it, is if you were to jump over the value you're looking for by picking up your finger or having an infinite discontinuity or a problem like that. But because we know this function's continuous, it must assume all values between a and b. Now, as I said, it's not really worth stressing too much about the formal definition, but let me show you an example that might make more sense for you. So what I'm trying to do is figure out if there's a solution to this graph 1, 0 on this interval from -2 to -1. So to show you that there must exist one, I'm going to substitute for f of -2. So the value is 32. You can verify this with your calculator. And if I stick in the value for -1, I end up with -4. So because f is a continuous graph, it's a polynomial, I must pass through 0. Oops, too far. I must have f of x equals 0 at least once in this range because I'm going from a positive of 34 to a negative of 4. And that's what the intermediate value theorem guarantees. So we could verify this similarly here. F of 0 is -1. F of 1 is going to be 2. And again, we usually abbreviate the intermediate value theorem as IVT just to save room. By the intermediate value theorem, f of x must equal 0 for at least one x in this interval 0 to 1. Okay. So again, if you're going from -1 to 2 on a positive or on a continuous graph, you can only do that by passing through 0. So again, intermediate value theorem is the technical term for it that guarantees it for us. Okay. For the next question, we know the intermediate value theorem applies because this is a polynomial, so it must be continuous. So now that we know the graph's continuous, and we want to verify that there is a solution, what we can quickly do then to see if there is one is we can evaluate it at 0 and 3. So at 0, we get a value of 8, and at f of 3, we get a value of -1. So because this one was positive and this one is negative, 0 must be somewhere in the middle. So I know that there is a solution between 0 to 3 for the answer to this question. So we can find it and verify that it did in fact exist by solving the equation. But that's one reason you might want to use the intermediate value theorem, is you may not want to go to all the work of solving without verifying that there actually is a solution. So let's take a look here and see what we get. So I end up with x equals 4 or 2. And this is the one that the intermediate value theorem guaranteed because I have to be within this range from 0 to 3. So I know that even though there's two answers, this is the one that I was looking for that intermediate value theorem says the function has. and I'll just abbreviate that. So one last thing that we may do to help show we understand continuity is to make a function continuous. So for example, in this one here, it's similar to what we did verifying the continuity, but now we actually want to choose a value, and here's where it'll happen. Is right there we'll pick a value for that constant to make this graph continuous. So I have, first of all, I need to make sure that the limit as I approach 0 from the left is equal to the limit as I approach 0 from the right. So in other words, what I'm saying is at x equals 0, I want 4 sine x over x to be equal to a minus 2x. Okay, so in other words, I'm looking at where the limits are the same. What value makes these the same? So you may already you may already remember this one. So that gives me the left-hand side is equal to 4. And when I substitute x equals 0 into here, I get a equals 4. So if I was to choose a value of a equals 4, then I know that the left-hand side and the right-hand side will be equal, so therefore the limit exists, and it will be equal to the value of the function, because at 0, that means 4 minus 2x. We can just verify this. Is 4, and the limit as x goes to 0 from the left-hand side is also 4. And if I was to take a look, what is the value at 0? I'm using this one here, which again we know is already 4. So limit exists and it has the same value as the function, therefore it must be continuous. So choose a equal to 4.